So it's our pleasure to have Zhang-Wei Hong here to present his research. And Zhang-Wei Hong is a PhD candidate in MIT, and he received his Bachelor of Science and Master of Science from NTH, National Tsinghua University in Taiwan. And he has conducted research and internship at TU Dundas in Germany and preferred network in Japan. Zhang-Wei's research interests lie at the intersection of reinforced learning optimization with a focus on developing principal algorithm to improve the usability of reinforced learning in real-world scenario. His work have been published in top-tier conferences such as NeurIPS, ICLR, eCora, and Cora. So yeah, the stage is yours, and we are looking forward to your talk.
Okay. Hi, everyone. I'm Zhang-Wei from Imparable AI Lab in MIT. I'm advised by Pokia Gurawa. So I will present two of my recent works in reinforcement learning about collecting and exploiting data in RL. Because this is a robotics seminar, so I would like to set the context in robotics first. The video on the left is from our lab. It is about controlling a robot hand to reorient objects using reinforcement learning. The video on the right is a quadruped robot controlled by a policy learned using RL. Sorry, I should mute it. Yeah. Reorienting objects with hand facing downward is very challenging because of the gravity. Running on terrains with gravels is also challenging due to the unpredictable dynamics, right? But you see, reinforcement learning nowadays has already demonstrated amazing locomotion and manipulation skills in these challenging tasks that were pretty difficult for modeling dynamics and model-based planning method. Okay, those amazing demos are all powered by reinforcement learning. Now, I will talk about the challenges we will be facing in making this application of reinforcement learning work. I personally, everyone knows RL, but I will still briefly talk about the problem setting here. The goal of RL is to find a policy pi maximizing the expected return J of pi through interaction with the environment. The expected return is the sum of reward over time. For example, the reward in object reorientation is simply just a binary number indicating if the object is in the target orientation or not. The reward for locomotion is just velocity and the stability, whatever that will make a quadruped robot running faster. Different from supervised learning, the training data for RL is from interaction with the environment. RL first has to explore the environment, trying a policy and collecting interaction history with the environment and improve its policy. And the stage of improving policy, I will call it exploitation in this slide, because we are trying to extract the information from the collected data and use those information to improve our policy to get more rewards. I will first talk about the challenges in exploration first. In the context of the locomotion and the manipulation, exploration is about trying your ways, trying your robotic arm and find the better strategy for reorienting objects. And in locomotion case, exploration is about finding a better gate, moving on the complex terrains. Concretely, it's just you run a neural network policy, taking state, and generating control actions, and execute this control action on the robot, and update the neural network based on the feedback from the environment. For example, you try one controller to run on terrains, and if you fall down on the ground, then okay, this policy is not going to be good. So you will just perform gradient descent, whatever, to update the weight on your policy. Okay, so exploration in RL is oftentimes abstracted in a process of searching for reward in the space. To start, consider the following maze. We have an agent represented by the blue triangle, and we would like to learn a control policy pi e that gets the agent to the top of the map. To do this, we give the agent a reward if it reaches the goal. And we use reinforcement learning to find the policy that maximizes the collected reward. So you can think of the blue dot is just the high performing gate for moving on the terrain, or the high performing strategy to move on the to manipulate the object. And this maze is like the parameter space in your neural network weight, and you're kind of controlling a policy to find a higher weighting, find a weight with higher rewards. And this type of setting is pretty can capture many challenging real world application, because it's very hard to define the reward. So usually you can just you always give the reward to the agent when they really achieve the desired outcome. For example, you only give the reward for when the agent reoriented the object successfully, right? This type of setting we usually is known as sparse reward setting in reinforcement learning. Now, what usually happens when we train a policy with a sparse reward is that the agent doesn't find the goal with random exploration, and therefore training fails. One solution, which is very common in robot learning, is to place more extrinsic reward and create a dense learning signal that the agent can easily follow to find the goal. While that's very feasible in this toy example, defining dense rewards for more complex tasks is nearly infeasible, and it requires a lot of manual tuning and a lot of domain knowledge on the robot and the task. So here I will show you one of the robot learning example of hacking the reward function to make tasks easier. So this table is the reward function term used in the locomotion example shown on the slide. So they just take the linear combination of all the reward and sum them together as the final reward to the policy. So you see, we only care about the task reward, which is the velocity tracking reward at the top of the table. However, in practice, you'd require to incorporate thousands of the task irrelevant reward terms to make this policy learning work. Also, you have to tune those magical coefficient of each reward terms. And usually that takes a few weeks or a few hours to find a good, to find a good combination of the reward terms and those corresponding coefficient. Okay, so what we know is that typical RL algorithm perform well when the reward function is very dense, and but they tend to fail on sparse reward tasks. These two learning curves are from common RL benchmark in Atari, but I will omit the task details because they are not related to robotics. We just need to know these two tasks present the nature of a sparse reward and a dense reward. So another idea to improve performance in sparse reward setting is to generate intrinsic reward, which incentivize the agent to be curious to explore new states on in the map. So at the start of the training, every state is new, right? Intrinsic reward will be spread across all the map and provide the dense learning signal for the policy to update. While collecting those intrinsic reward, the agent can find the extrinsic reward at the goal and solve the task easily. intrinsic reward have been shown to be very helpful when solving sparse reward tasks, like the Atari game Multimass Revenge, you may know. Yeah. The issue with intrinsic reward is that they are not always aligned with your task objective. For example, in this scenario, the extrinsic reward are close to the starting location and easy to find. But because the agent is curious, it can get distracted by the intrinsic reward on the right and therefore follow them to the wrong way. In this setting, it will be much better to train the policy without intrinsic reward and have the agent to learn the policy without distraction. This inconsistent performance is also why a plethora of intrinsic reward have been proposed in the past few decades, but none of them becomes the standard practice in the RL library, and none of them consistently perform better than naive exploration strategy like epsilon greedy. What this tells us is that intrinsic reward can actually hurt the performance in dense reward tasks. So this unpredictability is an issue that prevents practitioners from using intrinsic reward in any on a wide variety of new tasks. Prior work usually scale, because they still want to use intrinsic reward for to solve the task, right? So they have to tune the balance between intrinsic reward and the extrinsic reward carefully. So what they usually do is to scale the magnitude of intrinsic reward with a constant scaling factor, lambda. But oftentimes they needed to tune this lambda for every new task. So, this is not a practical solution to address this problem. To address this problem, we propose a method that enables RL agents trained using intrinsic reward and the extrinsic reward to perform well on both sparse and the dense reward tasks. So, okay, I'm going to present a exploration method working well in both hard and easy exploration tasks. This is the method proposed in our NeurIPS 2022 paper, redeeming intrinsic reward via constraint optimization. So our method achieves this by using intrinsic reward only when they can help a performance. We train two policies. The blue triangle represents a policy trained with only extrinsic reward. And the pink triangle represents a policy trained with both extrinsic and the intrinsic reward. We usually call this pink triangle as a mixed policy. We propose using the following constraint in order to train with intrinsic reward beneficially. The mixed policy, which is the pink triangle, must collect more extrinsic reward than the extrinsic reward only policy. So the intuition is that if you train with intrinsic reward, then you have to get better performance than the policy trained without intrinsic reward. For example, you can think when you train a policy to play a video game, or train a robot to walk on the terrain, you have to balance the robot's curiosity on exploring new strategy and the reward maximization objective. Otherwise, that one possibility is that the robot will get distracted by curiosity, and they just keep exploring thousands of different walking gait and the locomotion strategy instead of maximizing the best walking strategy they find before. This is the main idea behind our method, which we call extrinsic intrinsic policy optimization, or IPO for short. We train a policy to maximize both rewards, subject to the constraint we just showed in the previous slide. This constraint states that the intrinsic rule should be only used if they help the agent to achieve higher extrinsic reward. Now, the question is, you see here, this is we don't have the solution for the max pi e in the constraint, right? So we first we can first convert this problem into Lagrangian dual problem, and then we can solve the Lagrangian multiplier during optimization as well. The alpha in this equation is Lagrangian multiplier. Okay, and I will talk about its interpretation in the next slide. So we can arrange this equation so that the role of alpha becomes clear. So you see, now the problem becomes, you just the alpha can control the importance of the extrinsic reward in policy optimization. And these two objectives can interact to each other based on alpha tuning. Okay, I will show you later. But these two objects can interact with each other by policy improvement reformulation. But okay, I think we can talk about that in a later. This might be a too technical detail. So the final tractable algorithm is repeating these 3 stages during training. We first train the extrinsic policy for a few episodes, which we solve the policy on the policy that may only maximize extrinsic reward. And then we switch to train the mixed policy for a few episodes, and update the Lagrangian multiplier, and then start over again. Okay, and so that's it. Our whole algorithm is just repeating these 3 stages. And let's see how this algorithm works in this toy example first. So the gray triangle is the agent controlled by our policy, and the red dot are randomly initialized at every episode, and therefore the red dot will constantly generate intrinsic reward, so that the agent could get distracted. So that's why we call it distractor. And our goal
is a question.
Yeah, okay.
So I'm just out of curiosity. So what kind of intrinsic reward you use in this paper?
Oh yeah, I will talk about what we use in the next few slides.
Okay, and
yeah.
I have another question. So is the intrinsic reward module trained and at the same time as well as the policies?
Yes.
So it is possible that because your intrinsic reward is keeping change, so the whole train process become very unstable.
Yeah, it's possible. Yeah. Okay. Oh, but that's how intrinsic reward is designed. Because intrinsic reward are usually designed to capture novelty of state, so they want the intrinsic reward on every state to decay over time. However, it's not the case. The intrinsic reward the intrinsic reward value on every state is usually going up and down over time, so it doesn't really capture novelty very well.
I see. Thank you.
Oh, okay. So this plot at the top is the performance of each method. The black curve only use extrinsic reward, and the red one use both. The blue one is our method optimizing both rewards using IPO. The plot at the bottom is the evolution of Lagrangian multiplier controlling the importance of the extrinsic reward in optimization. So we see that following extrinsic reward is actually better in this environment. So you see the black curve reaches the maximum performance, which is nearly 400 in around 0.4 million of frames. The alpha decrease initially, but decreasing rate is getting smaller over time. This implies that initially the agent is trying to exploring the environment, and after the agent realized that the exploiting extrinsic reward is better, the agent start upweighting extrinsic reward. So what we will see is that after the middle of training, we see the performance of our policy increase, and the star outperforming the red curve, which is the policy trained with both reward. Meanwhile, we see the alpha also start increasing, which means that the importance of the extrinsic reward is getting more important, and the extrinsic reward start taking over the optimization. Now, I'm going to show you some more interesting result. This is the result in Atari, all of the 61 Atari games. So I'm going to show you that IPO is a better go-to choice for applying RL to any new tasks. So we compare IPO with the baselines using average probability of improvement across all the Atari games. So why do we choose probability of improvement to evaluate IPO instead of aggregated mean returns? So first, probability of improvement, it was a statistical metric proposed in one of the recent RL evaluation paper. It is a recommended way to evaluate RL algorithm. And another reason is that it's because we want an algorithm mostly performing better than naive exploration strategies, right? This is an important metric for a new algorithm. Imagine when you apply RL to a robot application, the reasons that make you choose a new algorithm instead of the old ones is that the new algorithm performs better than the older ones most of the times, because you don't want to try out multiple different algorithms and figure out which one is better. You want an algorithm that always or usually works out better. As EIPO, as IPO balance extrinsic and intrinsic reward for us, it allows us to use intrinsic reward for any new task, regardless of the task property. So we use IPO, we use PPO as our base RL algorithm. And so here, this is how the intrinsic reward we used across all the paper, which is R&D. We compare this three settings: PPO trained using only extrinsic rewards, and the PPO trained with both extrinsic and the intrinsic reward, and the PPO trained using IPO to balance both reward functions. Okay, first, we see that PPO and with R&D only has a 50% of the probability of improvement over PPO. So, this suggests that adding R&D to PPO is not necessarily better than PPO on average, because then 50% implies that you sometimes get better result, but you sometimes get a bad result. So it's just, you throw a dice. In contrast, IPO can achieve a substantially higher probability of improvement than both PPO and PPO with R&D. So this indicates that our method outperforms both baselines in a majority of trials. So what I mean by outperforming in the majority of trials, this is saying that when you randomly pick one task and one random seed, IPO is most likely to perform better than the naive exploration strategy like PPO and the PPO plus R&D in this new trial. Okay, and you might be wondering, maybe we sacrifice the performance of R&D in those hard exploration games, but it turns out it's not true. We actually preserve the performance of R&D and slightly performs better than R&D in the games where R&D beats PPO. Okay, then the follow-up question will be, one can still argue that, okay, I can tune the scaling factor of R&D, and probably we can find a single lambda factor that make R&D to match PPO most of the times, right? This is a fair argument, but the answer is that it's not always true. The plot shows the game score, which is the extrinsic return in one of the Atari games, obtained by our method and highly tuned R&D. So PPO that is trained with only extrinsic reward is the black curve. R&D is the red one, ours is the blue one, and the rest are the tuned R&D with different lambda, which is a scaling factor of the intrinsic reward. And we see that IPO still, the IPO is the blue curve. You see, it still matches or exists all of the tuned R&D result. And actually, by tuning the scaling factor of R&D, you sometimes even get a much better performance. For example, like the purple curve. You only get a very marginal improvement by tuning the lambda coefficient. And this result also applies to other environment as well. So this is the environment we evaluate for tuned R&D. We evaluate in total 6 tasks, and this result suggests that IPO can remove the effort of tuning hyperparameters for R&D, while it's still outperforming PPO more consistently. Yeah. Okay, then I guess the final follow-up question will be, okay, why IPO can even outperform tuned R&D? Because we simply just training a additional policy over R&Ds, right? And probably what's the other factor that can make IPO better than R&D? So one possibility is that IPO can adaptively tweak the importance between intrinsic and the extrinsic reward online. But tuned R&D can only fix the intrinsic reward scaling from very beginning. So
I ask a question.
Sure.
So when you optimize policy intrinsic and policy extrinsic and extrinsic, and do these two policies share the same set of trajectory during optimization?
Oh yes, but it depends on your choice of the base algorithm. So in our paper, we choose PPO. So this is on policy algorithms, right? So we actually we collected one trajectory using pi e plus I and one trajectory using pi e, but we collected trajectories using one policy at a time. They just alternated to collect trajectory over time. And both policy will be trained on the same trajectory. And so for example, if pi e plus I collected the trajectory, then pi e plus I will be trained using usual PPO objective. But pi e, which is the policy that doesn't collect the trajectories, right? It will training pi e will require some of policy correction. But the details, I can talk about details afterward, but you can find those details in our paper as well.
Okay, so why don't you collect two set of trajectory with the policy essentially, so that you can optimize these two policy parallel?
Oh yeah, that's a fair question, but we also care about sample efficiency. So if you collect the trajectory by using two policy every time, then you will need a double amount of the trajectories, right?
Okay, that makes sense. Thank you.
Yeah. So this is the evolution of Lagrangian multiplier of our method IPO in all of the Atari games. Remember, the scale of Lagrangian multiplier is the importance of extrinsic reward. in general, we see that the Lagrangian multiplier increases over time, which is expected because extrinsic reward should be more important after exploration is finished. However, interestingly, we see the Lagrangian multiplier in some environments goes up and down. This is an example from the game Sequest, which is one of the other game. IPO actually outperforms R&D in these games. This is interesting. So first, IPO is the blue curve here, and R&D, the policy trend with R&D is the red curve, and the PPO is the black curve. So IPO outperforms R&D in this game. It's interesting because RL practitioners usually believe that the agent should spend less time on exploration near the end of the training. And that's why people decay epsilon value in epsilon greedy linearly over time. Epsilon greedy is one of the exploration strategy used in DQN, deep Q network, and the epsilon controls how much random action you will pick during exploration. So initially, people usually set epsilon to be a very high value, and then they decay over time because they want the policy to be very deterministic, very greedy near the end of the training. However, our results may imply another interesting fact that adaptively tuning the tendency of exploration may be beneficial on exploration strategy. I think that's an interesting message outside of this scope, but I think it can open some new door for exploration and exploration strategy design. Okay, now we have IPO that collects useful training data for us. Still, we need one good exploitation strategy to learn a better and a generalizable policy in the less amount of data. Since collecting data is more expensive, it's very expensive, can we extract information from data as much as possible? So we show that by leveraging the structure of the reward function, we can make RL algorithms more generalizable and sample efficient. So I will present how we leverage the reward function structure in our a.k.a. 2022 paper, Bilinear Value Networks. Okay, so this might be different from the abstract I sent out because I think you originally planned to present one of my offline RL paper, but I think this one, Bilinear Value Network, might be more relevant to this seminar, so I decided to make this change. So many tasks can be modeled as goal conditional learning. So I listed two papers from co-row this year. The left one trains a quadruped robot to work on based on the user specified get parameters, where get is just a goal of the policy. And the right one trains a policy to navigate the robot to the destination. This is the visual navigation paper. So in this goal conditional learning, reinforcement learning, we usually learn a Q network approximating the expected return of targeting at goal by taking the Q network approximates the expected return by taking action at a state S and then following pi for the rest of the time steps. The policy is then trained to maximize the expected Q value at the state collected by the policy. And concretely, Q value can denote the success rate or distance to or negative distance to the goal. And the policy is trained to maximize the success rate or find the shortest path. So in multi-goal reinforcement learning, sample efficiency is very critical since we hope the policy can be versatile and achieve all of the goals that we will specify. However, it's just impossible to enumerate all the goals, right? Because you probably the get parameter is a continuous space, right? It's impossible to enumerate all the gates. Also, it's also impossible to enumerate all the locations in the map, right? And we even sometimes hope that the agent can generalize to unseen gate and unseen locations. But that will if you that will take a lot of the data to train. So that's why we should we should care about sample efficiency in multi-go RL. So good sample efficiency actually need a generalization. So for example, given a state denoted as the blue dot here, we hope to learn a Q function predicting accurate values over all the goals denoted in the red block shown on the right. The green overlay indicates the Q value that we already learned. If the Q function generalized well, the number of data required is largely reduced. Because if you generalize, then you can generalize the prediction from a very few points to a large region, so that we just need to sample a few points on the red block. And if they generalize well, then you will get it will learn the correct Q values over all the goals in the red block. So typical method represented the Q function as the monolithic network. The state, action, and the goals are concatenated as a vector and feed into the network to predict Q values. Such a monolithic architecture does not generalize well because the state, actions, and the goals are jointly processed by a single neural network. Suppose we train our Q function by 2 samples, where each sample is a state, action, goal pair. The color denotes a different instance of a state, action, or goal. At the testing time, if you permute S, A, and G in a different way, that will be an unseen input pattern to the learned Q function, which may fail, where the Q function may fail to generalize, because this is an unseen pattern for Q function. As the monolithic network doesn't generalize to unseen combination of the state, action, goal tuple, we have to sample a large amount of the state action pairs to make every state action and goal pairs to the in distribution data for this Q function. And this is going to take you consume you a lot of data. So our idea is that we can actually improve the generalization using inductive bias on the value function. So our hypothesis is that decomposing the Q function into a local and a global vector improves the generalization. So consider you are at a state S, and think of the next step A to approach your goal G. Here we denounce the agent's movement as green arrows. The alignment between green arrows and the red arrows indicates how a local actions match the global direction to the goal. Therefore, the Q value can be viewed as the dot product between both arrows. The more aligned, the higher the Q value is. Okay, so this idea leads us to our method, bilinear value network, which is simply just parameterize the Q function as the dot product between 2 vector fields, F and phi. And both vector fields are represented as a neural network. Suppose a decomposition such a decomposition will improve generalization. Suppose we train our Q function by 2 SAG tuples and then learn both vector fields, okay? We tested the learned Q function with an unseen SAG tuple. And thanks for the decomposition, the sliced inputs are the seen patterns for both vector field F and phi. And then so you generalize to this unseen pattern. Okay, we evaluate our method's sample efficiency in fetch and shadow hand manipulation benchmarks. So for both domains, the tasks are moving the object to the goal positions or manipulating the object to the goal posts. The state space are just the positions and the velocities of the object and the arm or hand. The actions are joint velocities. our method and the baselines are both trained by DDPG with high sign experience replay. Okay, I will not talk about detail of high sign experience replay because it's just a technical trick for training goal conditional learning. We compare our bilinear network with the monolithic network in the full suite of this benchmark. But here I only list eight tasks of them. So the gray curve denotes the performance of monolithic network. We plot the success rate in y-axis and the number of training epochs in the horizontal axis. So we show that our method, denoted as the blue curve, bilinear value network, outperforms the baselines in terms of the sample efficiency and even a syntactic performance in some of the environment. Okay, I think the next this result about generalization is going to be more surprising. I think this is the key result of this paper. So we evaluate the generalization of the Q function by pre-training and fine-tuning the agents in different goal distribution. So we consider two types of goal distribution here, left to right and near to far. So by pre-training, for example, by pre-training the agents on the left goal distribution means that we only samples go from the left plane, and while we will fine-tune the agents on the goals on the right plane. So if an agent can fine-tune faster, that will means that the agent can generalize the previous prediction learned in the pre-training distribution better. So after all the method reach the same performance in the pre-training distribution, we fine-tune them in the another distribution and compare the fine-tuning performance. Okay, surprisingly, we see that monolithic network is unable to generalize to new goal distribution. So it fails to generalize in pick and place and in the left to right case and the near to far. Our bilinear value network, surprisingly, learns substantially faster than the monolithic baseline during fine-tuning. This is suggested that bilinear value network can generalize better to new goal distribution, and this fine-tuning performance gap is substantially large. And I think this is the key result for a key finding of this paper, because that shows that previous monolithic neural network just cannot generalize very well. Okay, it's time to wrap up these two papers in the overview I showed you in the beginning. So let's come back to this big picture again. So my previous NeurIPS work, IPO, balance curiosity and reward more effectively, hence collecting useful training data for the agent. But after gathering those data, we need the exploitation strategy. And my iClear paper, which is Bilinear Value Network, BVN for short, can learn a more generalizable value function from the data. And because in the exploitation stage, we care about simple, we don't want to use too much data because data collection is very expensive. So by having a more generalizable value function and a policy, you can save the amount of data you require because you learn from less and generalize to more. Okay, thanks. This is the end of my presentation. And I prepare some backup slides if you have a further technical question. Thanks.
So let's send Zhang-Wei's talk. And is there any question from Zoom or audience? So
I have one question.
Yeah, sure.
Thank you for the super interesting presentation. I was really fascinated by the work you did on combining the intrinsic and extrinsic rewards. One of the things that I was curious of, when you form the constraint optimization problem and then solve it via the Lagrange dual optimization problem. One of the, I guess, key properties of optimizing the Lagrange dual problem is that it doesn't guarantee that the constraints are always satisfied during the optimization process. It guarantees that they're satisfied on convergence, but not during the optimization process. So I'm curious, how do you handle that property of the problem in your algorithm?
Yes, definitely. It cannot satisfy it because it's just a soft constraint. But I think that is the issue for all of the constraint RL problems, because by formulating it as a Lagrangian, we cannot always ensure it's satisfied. However, I think in this problem, we don't necessarily need it to be satisfied. I think as long as we can use because the Lagrangian, the process of optimizing the Lagrangian multiplier is actually the main drive for balancing exploration and exploitation. So as long as the Lagrangian multiplier can tweak the relative importance between two policies, then I think that is going to help the exploration in the end, because we already show intrinsic reward has already showed they can solve the hard exploration problem. But then I think we just need to find a strategy to know when to stop using intrinsic reward and the trends to optimizing extrinsic reward. But we don't necessarily need the extrinsic policy to be optimal. We just need it to be better than the mixed policy in maximizing extrinsic reward. So in summary, I think whether the constraint is satisfied or not may not be very important for the whole optimization process, because we can always benefit from the adaptively adjusted balance between exploration and the exploitation during solving the Lagrangian multiplier.
That makes into sense. I would agree with that. But I'm just curious, for your particular implementation, do you train all the 3 steps you mentioned until convergence, or is it just like a hyperparameter you train for like an amount of epochs?
Oh, you mean how many episodes do I train for every policy, right? Or
no, so it's a question very deeply rooted in like the Lagrangian optimization problem of like when you do like when you optimize like the 3 steps of your policy, do you train the 3 steps until convergence, which theoretically guarantees the constraint is satisfied, or do you just train them for an amount of hyperparameter epochs?
Oh, actually, so I trained them until the gap. Let me see if I have the slide here. Yeah. Okay, I think I don't have that. Yeah. So I trained until the advantage between two policy is nearly 0, and then I stop optimizing alpha.
I see. So that's kind of like a mechanism to somewhat approach the constraint satisfaction.
Yes.
Okay, that makes sense. Yeah, that makes sense. Thank you.
I also have a question for the bilinear value network.
Sure.
So essentially, your idea is something like you're trying to decompose the relationship between a state and goal. So you use 2 networks, and essentially you're trying to set a constraint between these 2 networks with set a bilinear constraint, exactly, right? So yeah. I'm just out of curiosity, so it is likely that if you would like to decompose the relationship between a state and goals, you can just use maybe you could use a state of Q network that only takes state and action as the inputs, and use another Q network that's only take action and goes input and try to make sure that the later Q network can to compose the output of the small primitive network. Something
Oh,
like
so
Q
you
mixing
want
multi-agent situation.
thank you. So I guess my understanding is you want to decompose the Q of you want to decompose the Q network into the dot product between
Yeah, kind
for
of.
example, phi of S and the phi of A, right?
Yeah.
Okay, yeah. Actually, we have tried this. It doesn't work, and I will tell you one interesting fact. It's very important to include state in both decomposition. So if we scroll back to the yeah, let me see. I think this is a slide going to shit. Let me reshare the screen maybe. And I would because I would like to jump into the bilinear slide. Okay, this is our decompositions, right? F of shit. There's too many animation. Okay, F of SA and the phi of SG. So I didn't write that in the paper because I think that is just too distracting. But I will tell you the interesting fact is that initially we tried the F of S and the phi of F of SA and the phi of G, and also your idea F of S and some like a phi of A in other single Go RL tasks, but none of them work. And it turns out I realized that it's very important to include state when you decompose the Q function into the dot product between two network. So so you see that in F and the phi function, S are both the input for both functions, right? So if you remove, suppose if you remove S from phi function, then everything just crash. I mean, what I mean by crash is that it will underperform the monolistic network by a large margin. And so there was an interesting story why we make this choice. There was from some failure experiment, but we can talk if you want to hear. We can talk later.
Oh, cool! Awesome, awesome.
Yeah.
Oh, so is there any more question from the audience? If not, let's thank Zhang-Wei again for his inspiring talk.